All right, here we go. Another video on, this time, the law of sines. Now, the law of sines has what's called an ambiguous case. You look at these three triangles. The black pieces of information are what you are given. These are three different triangles that are obviously different situations. Well, in fact, one of them that's not a triangle at all, and one of them that's more than meets the eye. But the information I've been given in all of these is an angle and a side and a side, and I have to be careful about how I spell that out, you know. In the first one, I'm given an angle. Let's just estimate it at 30 degrees. It's some sort of acute angle. And whatever the lengths of these other sides are, this guy is just not long enough to make it all the way down to the baseline. No matter how I swing him down, like, he's not going to make it there. So given that information, I can't even make a triangle. The bottom one here is a right triangle. So it looks like whatever that is, this side length is just perfect to accommodate the other side length and the other angle. But on this last one, what I see here is I've been given an angle and a side, and it's this third side that's interesting. If all I knew was the measure of this angle, this side, and that side, how would I know that this angle is the size it is? What would stop that triangle from looking like that? These two sides would be the same length. I would have started with an angle, drawn a side, and then drawn another side. How do I know? This is what's called the ambiguous case. The ambiguity here is that it's not clear from the given information what my triangle should look like. So the information we're given is SSA, and what you should remember about SSA from geometry is that SSA is not a congruence theorem. Now what that means is that given that same information, I don't necessarily have one unique triangle. Let's take a look. All right, we're going to try a problem just using the law of sines. We're going to not even think for a while if this has anything special about it. The reason we know we're using the law of sines is because, well, it's right there in the directions, but also because we've been given A, and that usually tips us off that we're using the law of sines. Okay, so I've got a triangle drawn here, and I just start working it out. I set up my proportion. I multiply to get the sine of b by itself. And what I find here is that the sine of b equals 0.874. Now there are two different places on the unit circle where the sine of b equals 0.874. Think about it. The sign is positive in the first quadrant and the second quadrant. Maybe I'm at 0.874 here, or maybe I'm at 0.874 here. There are two different possibilities, and we're going to have to see if they fit. But at first, we pretend there aren't. So we go through this problem. We take the sine inverse of 0.874, and we get 60.9. Sorry about that stumbling. We subtract from 180, and we find that our third angle is 97.1 degrees. It's not exactly drawn to scale, but it's not awful. And then we just use the law of sines, and we find that the last side is 7.94. And it makes sense that that's the largest side out of the three of them. And that's across from this largest obtuse angle. But we have to snap back to reality here. If the first thing we find is an angle, we should assume that we are looking at the ambiguous case. If we find a sine that is, let's say, close to 1, that means that there are two different angles, possibly, that fit that bill. Now I say possibly because it's possible that the second angle we find won't fit in the triangle. More on that later. But it's also possible that that's a 119.1 degree angle. Now B doesn't look like a 119.1 degree angle, so maybe our triangle's drawn incorrectly. So the relationship here is that two angles have the same sign if they are supplementary, because they would have the same height in the unit circle. So if we do 180 minus 60.9, that's how we find that 119.1. If you check the sign of 119.1, you're going to get that same 0.874 number. Then we have to go through the entire problem like that. Hey, that fits with 22 degrees. What I mean by that fits is if I add 22 degrees and 119.1 degrees, I'm still not up to 180. I still have room in my triangle for the third angle. That third angle is 38.9 degrees, and that last side is 5.03. That's just using the regular old law of sines to find c there, little c. So what am I looking at? Well, what I'm looking at is that C is an acute angle, that side C is way shorter than we initially thought, and that angle B is larger than we initially thought. And what happens is that these two sides are congruent to each other. So A is congruent to A there. Okay. Here is officially how you know how many triangles you have. Sometimes you'll have none. Sometimes you'll have one. And sometimes, like we just looked at, you'll have two. Okay? The h here is the height, which is related to the sine of the angle given, kind of in the same way that we talked about in the last video. So just keep in mind, if the first thing you find is an angle, you should have the law of sines ambiguous case on your mind. All right, thanks for watching.